When you are.
Okay. So is there anybody in the room other than you?
Yeah, there's 3 people in the room.
Oh, excellent. Okay,
Plus me,
great.
4.
Okay, well, we got 3 people online, plus our facilitator and us. So we have.
And we will have the recording as for the webinars, so that's fine. Good, then welcome everybody for our adoption meeting. The first one again after a long break since we go back to physical again. Yeah, we are a pretty small crowd, so as Mark suggested, I guess we go through the agenda and take a look at what you're actually interested in hearing. Can I have the slide deck, please, that we prepared? Because we have a very elaborate agenda. Although, no, yeah. Which starts with a short introduction and welcome. And then oops. Slides are back. Mark, just to confirm online, can you see the slide deck?
Yeah, we can see it fine.
Okay, perfect. That's brilliant. So what we were planning to do is, apart from a short introduction and welcome, is I usually go through the recommendations that we have finalized a couple of years ago, just for those who are new to the working group to catch up with what the goals of the working group are, what the recommendations look like. And then we have kind of a Q&A session on the recommendations, so to clarify any whatever misunderstandings and discuss any issues that you might see with it. The second part that we were planning to present at this plenary was a major paper that came out last fall, which basically summarizes which summarizes the recommendations and then all the reference implementations and all the pilot deployments that we've had so far. So it's really a nice survey of how different institutions implemented the recommendations and rolled them out actually in operational infrastructure. So that's something we are actually very proud of, because I think we're one of the few working groups that actually made it from putting out recommendations to actually seeing wide-scale technical deployment and implementation, which is way more difficult than adopting a statement or signing up to some principles. And then I wanted to briefly present some of the new developments that are going on in terms of adoption. So we have a new reference implementation for RDF data, something we didn't have so far. Then there is 2 new pilot systems that are being implemented that I'm aware of, and I'm aware of further pilots being developed, but none of them are here or could join the event for presenting them. So I hope we'll get them at some other opportunity. And then the last item is some new directions, and new in the sense that it's applying the recommendations in settings for which they were not originally conceived, but which are basically conceptually the same thing as what we were aiming for when we founded this working group, namely kind of being able to track and identify specific states of evolving data landscapes over time. And this is 2 new settings for information retrieval systems, where we want to make sure that queries set against such systems are reproducible. So you can track back which subsets of documents were available at a given point in time, satisfying a certain query, which sounds trivial, but unfortunately is not. And another issue that is gaining prominence as accountability requirements increase for AI systems, specifically online learning systems that continuously update themselves by the data they present, where we see maybe an opportunity that the same principles that we have for dynamic data identification can also help identify the state of a specific machine learning model at a specific point in time, to be able to go back to a specific decision made and track the reasons for it. So again, same goals and principles, namely transparency and identifying the state of data at a given point in time, but applied to very different settings. So that's the proposed agenda, pulling together the information that I've received when I asked people in institutions whether they wanted to present something. That's the menu that we can choose from. and we can have the full degustation menu and go from the first course to the last. But as Mark said, we're a pretty small crowd, so we can actually also pick out the stuff that you're actually interested in. And if all of us are familiar with the recommendations already, I can definitely skip the first part because that's identical to what we've heard.
So actually, Andy, we're up to 13 online participants, so people are coming in. So I don't know, we could do a quick poll to see if people are familiar with the recommendations, but maybe it's worth just going through the talk and see where we get.
So who is familiar with the recommendations? If that's 12 out of 13, then we might do a private interaction.
Raise your virtual hand in the.
I don't see.
Rebecca Koskela is, and
well,
I'm not sure she counts. With all due respect, Rebecca.
Okay.
I think you should go through it.
If for the rest of the audience the recommendations are new, I'll go through them very quickly and explain what the goals were and how we came to how we arrived at the recommendations, and then we'll take it from there. Okay, so we'll start with flipping slides, which doesn't work at the moment. Maybe I'm pressing the down button. It did work before. Maybe the focus of and it's blinking blue.
You have text.
No,
there you go. No, it goes. Yep, you got it.
Okay, so that's the welcome slide. I can go through that one very quickly. Now, short description of the recommendations. Basically, what the problem that the recommendations try to address is twofold. One of that is if you want to identify and cite data, that usually assumes that the data is fixed. So you have a data file that's static, then you can point to it with any persistent identifier, and when you resolve it, you get that file and we're done. The problem that we have in most modern settings is that research data is dynamic. So new data keeps coming in continuously, and even the data that has come in the past quite frequently go through error corrections, quality improvements, you fix problems with the data. So there's quite a lot of changes to a lot of the real world data sets that we are faced with. Now, the way that people have still cited such data streams and the way this problem was solved so far is either by just referring to the data stream and said, I got the data there. But that doesn't help us with reproducibility at all, because if the data changes, any study that you do 6 months later will be working on quality improved, but ultimately different data leading to different results. The neatest feature that I find when data is being cited is giving an accessed at date. So I downloaded the data on the 15th of January, which is lovely, but utterly useless unless it comes packaged with a time travel machine. Because unless I can travel back to the 15th of January, I still can't get back to the same data. And the only solution that so far has been working reasonably well is kind of an artificial versioning by freezing the data at certain stages in time. So an annual dump that is frozen. So you have the continuously evolving data, and then once a year, once a month, once a week, you freeze it and you store that as an additional data dump. So you have annual copies of the data. That doesn't scale terribly well if it's really huge data volumes with isolated changes here and there. And it also delays any kind of reproducible analysis that I can do until the next frozen batch is available. So any studies that are done in between on the live data stream are not reproducible, which is not very nice. So what we would like to have is a solution, a generic solution that allows us to identify the data at any specific point in time, not every quarter of a year or annually or whichever other interval we have. That's the first problem. So dealing with the dynamics of the data and the data changes. The second problem is the granularity of the data that we are working with. Data sources nowadays are huge volumes of data, And hardly any researcher uses an entire database or the entire data collection that's hosted by a repository for a study. You select a certain subpart of it. You select certain rows and columns from a table, a certain subset of files from a document collection or from an image collection. And what I want to do is I want to precisely identify that very specific subset. How is it done so far? Either you extract the subset of data from the database and you store it together with the study, with the paper that you have. So you extract whatever 50,000 images, satellite images, X-ray images, or query a database, you extract the data, and then you upload the data as a dump together with the paper. That doesn't scale terribly well if you have whatever, a 5-page paper with a terabyte of data, and then 6 months later you do a new study, and here is another 6-page paper with a slightly different version of, again, a terabyte of data. Plus you have thousands of data dump files that you need to manage ultimately. The other way, how this is being dealt with, is in the method sections of papers where you describe the process, how you extracted the data, how you selected it. And you say, okay, I downloaded data from these and those measurement stations in that province from the 1st of January until the 25th of March. And that resulted in 15,225 tuples, and these are the ones that I analyze. Now, for all of us who have tried to reproduce such a study and try to get exactly the same subset of data based on the description, will realize that this is sometimes quite an intellectual challenge, because the natural language description that we provide in the method section is usually not sufficiently precise to easily get to exactly the same number of tuples. In my example before, whatever 1st of January till 25th of March, does that include or exclude the 25th of March? Open or closed interval. Natural language is not precise enough. And so what we wanted to have is basically a method that allowed us to identify any arbitrary subset of data at any given point in time easily and without requiring intellectual puzzle solving for getting back to the same subset of data. So it's the dynamics of the data and the granularity, the subsetting that we are addressing in our working group. Working group was founded in 2014 and officially ended in 2015. We had the recommendations ready by then, presented them at the Plenary 7, which seems ages ago by now. We then waited a full year before endorsement because we wanted to make sure that the recommendations can actually be implemented and that they actually do work. Because on paper, things always look nice. Once you try to put it into practice, you might come into interesting challenges. And so finally, by 2016, we had enough evidence collected from different pilot adoptions, very early reference implementations, that we felt confident that this would work. And what we've done ever since further affirmed our assumption, because right now we have been going not only through pilot adoptions, but really through really deployed infrastructure that are using those recommendations. And you'll see some of them in a minute. But let me first tell you a little bit about how the recommendations actually work, so what the solution is. And the solution is actually trivial. There is no rocket science behind it. It's not inventing new concepts. It's all using things that have been around for decades. So basically what we have is data. And when I say data, I mean any kind of data. Can be a relational database, can be a comma-separated value files with rows and columns. It can be a directory with thousands of scanned images. It can be a multidimensional data cube. Can be a single image that you use as data. And we have some means of accessing that data. Accessing can be an SQL query. It can be a list directory command. It can be drawing a bounding box around a certain region on an image, or it can be drawing even a specific arbitrary shape on an image to select a certain part of the image. So whatever it is, it can be identifying a subpart of a graph in a graph structure database. Let's call that a query, whichever way it's then technically implemented. So even a bounding box basically is a query onto the image pixel range, so to speak. So we have data, and we have a way to access that data that we refer to as a query. What the dynamic data citation actually does is it cites dynamic data, but that's not where the dynamic comes from. It cites it dynamically via a query. So how does this work? When we have data that is evolving over time, we need to make sure that we can go back to earlier states of that data in time. That process is called versioning and has been around for quite a long time, no new concept. So what we need to make sure is that whenever we do changes to the data, that we don't overwrite the earlier state of the data, but that we mark the earlier state as invalid, starting from a given point in time, and that we then insert the new value again with a timestamp. So you have a database, new tuples keep coming in, new images arrive. You store the timestamp when the data became available in the database. You delete something in the database, you don't physically delete it, but you mark it as deleted with the deletion timestamp. If you find an error in your data, you don't correct it and override it, but you mark the erroneous value as deleted with the timestamp, and you reinsert the corrected value with the new timestamp. Basic principle of data versioning and timestamping, no rocket science. If now a researcher creates a working set, a subset of some database to use for a study, for an analysis, via some interface, can be drawing bounding boxes, can be setting of SQL statements, can be face-setted browsing interfaces, whichever way researchers would usually build and select their data. What we then do is, once they press go, give me the data, that usually issues a query to the database, the file repository, the graph, whatever you have as a baseline. We store that query with the execution timestamp. And we assign a persistent identifier to that query. And so by having a timestamped query and a timestamped and versioned database, you can at any given point in time later on rerun that timestamped query against the timestamped database to get back to the original data. And that's where the dynamic citation actually comes from. We don't cite any physical manifestation of the data, but we cite the query that identifies the respective subset of the data. This might sound complex, but it's basically what we are doing all the time when we are calling up a file from a directory on a computer. Because the file on the computer hard disk is not a continuous stream of data, but it's actually distributed across different sectors, across a RAID system. So what we refer to as a file name is basically a query that gets the individual sectors, pulls them together, and delivers you the data stream. And I saw there was a hand up here. Do you have a question or?
And now the query is like an entity?
The query is basically the entity that we store. But for the user, it's transparent. The fact that you're issuing a query on a file system whenever you click on a file name is completely transparent to you. For you, you're opening the file. For the researcher, they get a DOI, a URI, whatever, a persistent identifier. They refer to it, and they get the subset of data that was used by the researcher originally. How it's being done is completely transparent. But technically, yes, it's a query, and the query is the entity. The recommendations go a bit further. We have some discussion on different types of timestamping and what timestamp to assign precisely. There is some rewriting necessary if you want to really ensure that you not only get the same subset, but that you also get it in the same sorting order. If any further processing depends on the sequence of elements being presented. So there's a few further aspects in the recommendations that address those issues. We recommend to store some hash values for verification purposes, because you might run in a situation where you physically have to delete data by law. And then obviously you need to have the information somewhere that the information is not reproducible, because you're not allowed to keep it reproducible. So those are things that are also addressed in the recommendations. But in a nutshell, the core principle is timestamped and versioned data and storing a query with its execution timestamp to get back to the data. And for the user, again, nothing changes. This is completely transparent. It's happening in the background in the infrastructure. So when a user basically then accesses such a subset of data they collected, they get a persistent identifier that they can use in the paper. That persistent identifier can also be directly an input parameter to any processing script, because it can machine actionably be resolved to get access to the data. If you resolve the PID, it goes to a landing page. And here's a few neat benefits that we found from these recommendations that were not that obvious initially. The fact that Oops. Click. Not moving again. See. That one, yeah. Having the query string provides a very precise technical description of the subset that was selected for a specific study. So no matter what you write in the methods section of the paper, no matter what you think you selected as data, here you have a clear technical description of the selection process of the data. And there is even now some works going on, and how can we turn this actually automatically transcribe the query into a method section natural language text describing what you actually selected. So taking a work off the shoulders of the researchers. That's one nice thing. The other nice benefit, as opposed to, oops, that was too fast, is that you can obviously get the original data again. You can run the timestamp query against the timestamp database and go to exactly the same version of data. But you can also run the query against the current state of the database, and you get a semantically identical subset of data, but benefiting from all additions and corrections that have happened since. So if there is errors discovered in the data and they have been corrected, you can rerun an earlier study, rerunning exactly the same query, only with the current timestamp, which of course will get a new persistent identifier because it's a different subset that has now new data in it. And you can also do a diff. So what has changed since the last time that that subset has been queried and been used for a study? And this is actually a pretty nice characteristic. Another nice thing that we found out during the discussion is that this citation also allows you to cite the empty set. You can also provide evidence that there was no information satisfying certain criteria in the database at a given point in time, which might not be needed very frequently, but which is a nice feature that you can't do with any dump files by storing an empty file that easily. And last but not least, we found that some data centers actually found it quite useful. Need to press long, I guess. Yeah. Oops, that was too much. Going back one. That it's quite useful for data centers to see which parts of the data are actually being used. And we are now investigating this specifically in a citizen science project where we want to, and there has been a study in Australia already some years ago, where basically such a setting allows you to also identify where has my data been used, because I can use my data entry, run it against all the queries in the query store and find out which studies have been using my personal data, so to speak. So those are all neat side effects of this dynamic resolution. As I said, the recommendations, there is 14 of them. Recommendation 1, 2, and 3 are the basics: data versioning and timestamping, and setting up a query store where we store all the queries. Then there's a few recommendations on the actual process that is happening. So when a query should be persisted, check that the query is unique, because you don't want to have two identical queries that lead to identical subsets having two different PIDs. If the subsequent processing depends on the order of the records, and the database system underneath is basically a set-based one, so it returns results in random order, you need to address stable sorting for reproducibility purposes. There is a hash key on the result set, so to verify whether the recreated subset is identical to the original one. Some recommendations on query timestamping that also consider some privacy concerns. Recommendations on how and when to issue a new persistent identifier. Recommendation 9, obviously, store the query in the query store. And recommendation 10, provide a citation text directly to the user so that it's actually easy to then cite it. Resolving a PID should lead to a landing page. Obviously, no surprise here. And recommendation 12, we're doing this mostly for machines, so there should be machine actionability as well, because we want this system also to support automatic meta studies and machines basically working with the identified data. What happens if the technology changes? Nothing stays the same forever. If we migrate from one database system to another one, Recommendation 13 and 14 address these. Recommendation 13 says if you migrate from one representation of data to the new one, you also should migrate the queries accordingly, assuming that the new representation is at least as powerful as the old one. And recommendation 14, because we didn't want to end up with 13 recommendations, because some people thought it was an unlucky number, said if you do such a major thing, such as changing a complete data infrastructure, check whether it actually worked out. Again, should be a no-brainer, but it allowed us to add a nice 14th recommendation, and we're happy. Question?
Are you happy to take questions now, or do you want me to wait for the end?
Any point in time.
All right.
We're flexible.
I think you might have to repeat the question.
Yeah, I'll repeat it for the audience.
I'm not really into databases, but if I understand things correctly, these recommendations, they mean that you have to think very carefully before you set up your database. Or the recommendations that you are providing here, do they work on any given database?
So we will have a few. So the question was whether the recommendations work on any given database, or whether there has to be specific design decisions that have to be taken into concern before setting it up. So the answer is so far, and we'll see a few examples later on, we've found it to work in any setting. So we have done it for relational data, we have done it for CSV files, we have a pilot for file systems, it works for source code. We had one XML database being addressed in a reference implementation. We'll now see an example for RDF. So far, we haven't found a situation where it did not work. How you do it will then depend on the specific characteristics of the data. So the volume, the speed of updates, the number of queries. There is 3-4 different ways how you can version, for example, relational databases. History table, integrated, hybrid approaches, all have the trade-offs, trading space for performance usually. Do you need to think about it beforehand? Yes, to a certain degree, because you need to make sure you keep the timestamps. And yes, because you're not allowed to delete, but you only mark as deleted with a timestamp and add to it. So those functions need to be considered beforehand or added to it. In some cases, this is trivial because for databases, there is the concept of temporal databases. So you just need to turn a table into a temporal table, and it's done almost automatically. For other things, you need to physically add that feature. But we found out, so we once had a case study where we were also invited to advise on how to implement it. And we talked to the data steward and they said, okay, we will need to talk to our IT guys on this versioning because they were afraid that adding this timestamping and versioning would be very complex. So we presented this and the IT guy said, well, we never told anybody, but the database is timestamped and versioned anyway, because we wanted to make sure that we don't lose anything and just as a safeguard. So what was seen as one big problem by one side has already been done, but never talked about on the other side. So, but we'll hear more about those case studies in a minute. So what do we have? For those who are really short pressed for time, there is a 2-page flyer that summarizes the recommendation. A single sheet of paper printed on both sides that is very neat and is basically the gist of it. Then there is a slightly longer, I don't know, 6-page or 8-page report that we published in 2016, immediately after the recommendations were provided, that explained a little bit of the background thinking. Probably not as relevant anymore because we now have the last report coming up that Mark will present in a minute. But that was basically a more detailed description to that single page flyer. Then what we have as resources is a number of webinars that have been recorded from different settings, different data centers that have implemented the recommendations and that talk about how they did it for their type of data, how they handled specific, because not all of them implemented all of the recommendations. For some, the sorting was not relevant. For others, the timestamping was done in different ways. But there is examples for different types of data. We have NetCDF files in climate sciences. We have relational databases. There's a range of them available. So what I would invite you to take a look at that one that is closest to your own setting, and basically we can learn from those lessons. And this is the right keyword because when it comes to lessons learned, we have now tried to summarize all that we have learned over all those years since the recommendations were published and put that into a piece of paper that was a long time in the making. That was published last fall in the Harvard Data Science Review, open access. And here is where I would hand over to Mark to run us through what the paper actually contains. Is that okay with you, Mark?
Yep. Can you hear me all right?
Yes, we hear you perfectly fine.
Okay, great. Yeah, so as Andy indicated, this was kind of a culmination of a lot of work. Andy calls it our opus magnum. And it really is, I think, a nice comprehensive overview of everything that the working group has been doing and the lessons that we learned out of it. And so, and the first thing to note is there are 15 authors, and every single one of those authors actually wrote something. I mean, so this is really a group effort, and it really reflects a broad perspective. So the paper, outlines the principles like Andy just did. It goes through some reference implementations and then goes into more detail over adoptions and case studies, and then presents some lessons learned. So let's go through it in a bit more detail. You want to go to the next slide, Andy? Yep. So we have a large number of adoptions. These are not all necessarily spelled out in the paper. We go into detail for the really robust ones, but it's worth highlighting some as we go through them. So first off, these aren't just being the guidelines aren't just being implemented in archives and data centers, but they're actually being referenced in other standards and other specifications. So first off, they're not referenced in the Joint Declaration of Data Citation Principles because they came out after that, but it's, I think, critical to recognize that what we're really trying to do here is address Principle 7 in the Joint Declaration of specificity and verifiability, so that we can specify exactly the data used and verify that that was the exact data used. The Earth Science Information Partners, ESIP, has developed data citation guidelines, more than a decade ago, and they've fairly recently updated them. And they explicitly reference the RDA guidelines for referencing dynamic data. This ISO 690 is a bibliometric standard, and it also references these. We're still hoping, it's been going on for a while, the European Commission adopted a number of, no, actually it's not pending, Andy, is it? It has been adopted. Anyway, the European Commission has information and communication technology recommendations, specifications as they call them. And I thought ours was adopted. Is that not true, Andy?
I haven't received any confirmation yet. They have been, so basically it went through the process. There were no objections against it, but they haven't published the official adoption yet. So, and to the best of my knowledge, that is still pending. But if anybody has any knowledge about it, I'd be very happy to learn it.
Okay.
Off that box.
I think part of it is that Hillary Hanaho was really pushing this, and then Hillary Hanaho became Secretary General and had other things on her plate. But at any rate, it's very close to being recognized by the European Commission as a formal technical specification. And then DataCite also is addressed as well. So, and then we, as Andy indicated earlier, we did some reference implementations, sort of more conceptual implementations for different types of data sets, data storage mechanisms, data representations, as you can see here. And so that was useful. But what I think is intriguing is the next slide, that a number of actual databases, data archives have put this into place. So here's some early ones that they got started. And if we go to the next slide, these are the ones that have really done it in full bore. And these are the ones that are discussed in more detail in the Harvard Data Science Review paper. So if you really want to understand the work and the process that a particular archive went through to implement these recommendations, they're described in the paper for these adoptions here. I'll note that the last one listed, Deep Carbon Observatory, is not in progress. It is complete. It is deployed. And I just want to highlight, without going through each of them in detail, that they're covering all sorts of different types of data, but also all sorts of disciplines. So that's what the paper goes through, these case studies, and shows how this has been deployed. And then we conclude with some lessons learned. Next slide. And we present that as a frequently asked questions, because that's sort of what we get a lot is, Andy emphasized at the beginning that this is not difficult. This is not anything radical, but it does seem to be intimidating to archives. And so we wanted to sort of address these common questions that we get. And so the first one, do the recommendations work for any kind of data? And it appears so. So far, we have not found a black swan. So, we can't say definitively, but we've done a pretty broad array of testing, and it seems to work well. And even after the fact, for long established databases. Do all the updates need to be versioned? Versioning is always an issue for data centers. And yes, ideally, you would version everything. In practice, it doesn't necessarily work out that way. If nobody is accessed a version that was only up for a couple of weeks, there's no need to be able to maintain and capture that. So it becomes much more of a sort of a pragmatic exercise than a rigorous exercise of versioning. And as we'll talk about later, timestamping is perhaps more critical than the actual versioning itself. Can you delete data? Of course you can delete data. It's the same principle of, I think that's in the joint declaration. You can cite data that doesn't exist. There just needs to be documentation that it doesn't exist and that it's been replaced or upgraded or what have you. We recognize that archives can't store everything. So it's just applying appropriate due diligence. What types of queries? And so this maybe sort of sounds like any that a repository can support over time. That's actually, it sounds a little hand wavy, but it's actually pretty important because that support over time is the critical piece. If you're going to enable a certain query of your data collections, you'll need to be able to make sure that you can maintain that same sort of query in the future. But otherwise, as Andy was saying earlier, it can be any kind of query and seems to work. And you don't need to store every query. Does the system need to? You just need to store the queries that people want to store. So, for example, I worked on the Deep Carbon Observatory implementation, and you can query and query and query and come up with all sorts of sets. And it's not until the end, when you're finally satisfied, that you click a button that says generate DOI. And so the user decides what is relevant and what they need to put a DOI on, or any sort of persistent identifier on. And because that's what they want to reference. So you don't need to make an identifier for a query unless a user needs to reference that in the future. Any PID system can be used, as long as it's a good, globally unique, resolvable, meets all the needs of persistent identifiers. We tend to talk about DOIs, but any kind of handle will work. Even internal identifiers, as long as they're resolvable over time. Timestamping, do you need to synchronize across distributed repositories? No, as long as the local repositories maintain their own timestamps. So everybody just needs to maintain their own timestamps. You don't have to sync them up to keep them in line. Next slide. How does this support giving credit and attribution? I think it's important to recognize that we weren't really focused on credit and attribution, but it came up in the exercise of developing these that is an element of citation that people are concerned with. And so we recommend that you maybe have two identifiers, one referencing the entire collection and another referencing the subset, whereas the reference to the overall collection is probably the one for credit. That's the one that says, Jones et al. Created this data set. That said, Andy hinted at earlier, there has been some work in some cases where people have used the methodology to identify the particular people that collected subsets of a data set. So in a citizen science data set, you can identify, okay, I got this subset of, I forget, it was like ocean reef observations. And you can find out that Smith, Jones, Zhang, et cetera, were the ones that collected the particular data that you referenced. But I think it's important to note that credit is not really what we're focused on. We're really focused on the reproducibility aspect. And so that's the next point. How does this support reproducibility? And that's the heart of the matter. You know, it's precising the exact data that was used in the study, the exact data from the particular time. And this does not imply that the underlying data is publicly accessible and shared. You can reference private data, and you know, access is a separate concern from reference. Why should timestamps be used instead of semantic versioning concepts? You know, version 6.2 or whatever. Because there's no standard way to do that. And there's a lot of work in the community about how versioning works. And I think the conclusion is emerging really that what we're talking about is a provenance stream, not particular versions. And so that's why timestamps are critical. And that's why you need to be able to repeat the query as of that time. How complex is it to implement the recommendations? This is probably the overarching concern that we get a lot. And I'll talk about this a little bit more in a minute. And, you know, the answer is it depends. You know, it depends on how well organized your data are, how well you've been doing at versioning and timestamping in the past, and so forth. But it turns out it's not maybe as hard as you think it is. And that it's really just following on sort of basic data management practices of making sure that you know what data you have and when you got it. And then why should I implement this? Because it's the right thing to do. This is what science is going to need to do in the future. We're going to need to do more and more to be able to explicitly reference data used to ensure reproducibility and transparency of studies. So that takes us to the next slide. Just some big takeaways from the paper. The recommendations work. We haven't found a case where they don't work after many case studies, and I think that's pretty remarkable. Moreover, the archives that have implemented it have found that they don't necessarily need to implement all 14 recommendations to make significant improvements, and that you can do it incrementally, that it doesn't have to happen all at once. You know, you can pick and choose the recommendations you're going to implement over time. And everyone found value in doing it, even in adopting a subset of the recommendations, because they found that it improved their efficiency, it improved the services that they provided in some cases. They got feedback from the users that they liked it. It made for more efficient workflows. Overall, it invariably improves archive practices. Just knowing what data you have, when you got it, and how it's changed is just fundamental to archiving. And this really helps you with that. The technical migration piece, recommendations 13 and 14, you know, arguably that hasn't really been tested fully yet. You know, these recommendations have only been out for 5 years, and, you know, being able to repeat a query that was done 20 years ago, that is, you know, obviously untested, and but it's something that archives are going to have to grapple with anyway. It's a fact of life that archives have to deal with technical migration, and this just sort of forces you to think about it more seriously. As I mentioned, this is not really about credit. I think it can facilitate credit, but that's not what our focus was. I think credit is much more of a human concern, and we're really focused on the machine actionability aspects. And so this is the way of the future. We are going to need to be able to precisely reference data in the future, and not just for the purposes of reproducibility or at least transparency, but also workflows are going to become more automated, and dumb machines need to know the exact data that were used, and this is a nice way to do that. And I think Andy was hinting at that with some of the future applications that were unanticipated. So that's the paper overall. Like I said, it's rather a magnum opus. We encourage you to check it out. I think that's me, Andy, and back to you.
Sure, thank you, Mark. So just quickly, 2 more slides before we go into questions. But basically, here's a list of the webinars that are online, if you want to dive deeper into them. And basically, just a summary. It does work. It doesn't only seem to work, but it does work, and in a number of deployed settings, which we are very happy about. And with every plenary, I get more confident talking about it because we have more evidence that it does work, for longer periods of time. It allows people and machines to go back to the data that was used in a study. It provides automatic and for free the provenance information for the data, how it was selected, which subset was selected at what point in time. And we have information on the data usage in a repository. And the nice thing is it's a simple principle that works for any kind of data. You can extract source code from a Git repository at a given timestamp. You can extract data from a database, files from a file system. So the same principle works across all kind of characteristics. And that's, I think, what makes it really nice if we think about new process of how we do science, where we pull data from different sources, deal with the data using source code from different sources. All of that follows the same principles, and that's a really neat aspect. That's actually what the future ideas actually are pointing to in even more detail. So that's basically a quick run through the recommendations, how they came about, the problems and the solutions that are there. Now there's a few questions. So basically, do you have any questions towards it? Specifically, do you see any issues that make you think, no, this might not work in my setting because it's actually those issues that we were most interested in, because they allow us to learn where certain things might need to be adapted and changed. And the third part that I think is very relevant and interesting, if any of you is in the progress of or is thinking of potentially implementing these recommendations, be very interested in hearing from you. I just got a nice message to point something out. If you're located in Europe and eligible for European Union funding, and I don't know the precise regulations, but maybe somebody can help from the online audience on that. There is funding available for further adoptions of RDA recommendations. And who is it? Talia, would you like to say a few words on that, or on this by the EOSC Future project?
Hello.
Yeah, we can hear you.
Hello, can you hear me?
Yes.
Hi there. Thank you very much. I'm sorry, my name is Nejla. I'm working in RDA Europe with Ari Azmi. I don't know if Ari is in the room because I can't see Andy who's in the room. But if I may just say that in Europe, there's a very large project called European Open Science Cloud. There is a project called EOSC Future, which is implementing it. And RDA has a special role in the project to make these connections to the global data community and engagement. But one of the concrete things we have is a set of open calls, which unfortunately only Europeans can apply for. However, if you applied in the context of this group, you would all benefit. So it would have to be someone in a European institution. There is 50,000 available, and this is very much targeted at showing how concrete recommendations, which I've clearly seen in this group, can be implemented in the European Open Science Cloud environment at a cross-disciplinary level. So it's really bringing those disciplinary communities within the European Open Science Cloud. So there's plenty of room to define it how you would like. So I leave it up to the chairs to take that discussion with you further. I'll put the link to the call in the chat. And if anyone has any questions, I can answer them offline, but I don't want to take up your precious time in this meeting now, but I can certainly talk more to it, or if anybody has any questions.
No, that's
Thank you.
Perfect, thank you. So any questions, any issues that you see, any plans of using and applying it in the room or online? Yes.
I think we can maybe learn something just by, if it's a complementary question. We can learn, if you expect it to identify issues and you see that it works, and you learn again and again that it works. So maybe we can learn something about something new about the databases. We don't expect them like a query to be that helpful, but it is. So does it mean that the databases are more organized or more sustainable.
So, so I'm just repeating the question for the online audience. So basically what you're trying to is, do we learn something by applying the recommendations, whether it improves the quality of the actual data management that's happening, whether the databases become, whether we better understand how we manage the data and what we should do when managing data. And yeah, as Mark said, one of the lessons was that all data centers benefited from applying them, even if they only applied some of the recommendations, not all of them. Because yeah, I agree with your observation. I guess it does help us increase the professionalism of data management by having version data, by having those timestamps, by having documented the queries. It does professionalize also the research because it increases reproducibility and without putting additional burden on the researchers. So those are the benefits. And yes, I do think that overall it will improve the processes that we have in place.
Yeah, a few data centers even found that, I mean, some of it's not surprising that, you know, having a better understanding of your data and how it's changed over time is just essential. But a few data centers found that, oh, hey, we actually need to repeat queries sometimes. And this makes it really easy to do that. So it actually introduced efficiencies in ways that they hadn't anticipated.
One of the first adoptions actually did even the math of what it cost to implement the solution.
Yeah.
And how much money it saved in, or by what time it would have basically amortized itself, because they need to do a number of reproduction studies every year. And doing it in a conventional way, which means manually digging out the data, cleaning it again and getting it to exactly the same subset and setting up the same data feed, was quite costly. It cost, I don't remember the precise numbers, but I guess it was like 20 studies. After 20 studies, the cost of implementing it was cheaper than just continue doing it the conventional way, or at least it was in the order of magnitude. So whatever, a small two-digit number.
It was about that. And this is in the biomedical field where these things are done.
Yep.
More frequently.
From the medical domain, yeah.
We do have a question online from Vashti Galpin.
Yeah, hello, can you hear me?
Yes, we can.
Yes.
Oh, great. So I'm coming from this from a slightly different angle. I work in a programming languages group, and we've developed, we work on something called language integrated query. Essentially, it means you can interact with the database through the language without needing to work with the specific language of the database. But that's not the important thing. The important thing is we are now doing temporal database features in the work in this programming language. And certainly this has been a very interesting session for me to think about how we might support this within our work. I just wanted to mention that. I have a poster here about the work we do, and I'll put a link in the chat.
Thank you very much, Deb. That's extremely interesting, because it might, and I'm not familiar with your approaches, but it might even work in the opposite direction as well, I assume. So taking a structured query and mapping it back to natural language, is that possible as well?
I think it is, but I think it's outside the scope of what we do. Yeah. But certainly we could work backwards in the sense of having a functional language expression of the query, which may be a more general way to talk about it, regardless of what's actually going on in the database. So I think the power that we bring is to abstract away from the technical details. So that could be useful in this context.
Yeah. I guess my comment would be that for the actual query store, we would still need to store the query as executed in the very specific setup of the very specific infrastructure and database, because if the data is being migrated, those queries need to be migrated. But having the dual link between the natural language expression, which is basically the intention of what the researcher wants to select, and it's phrased in a researcher's language, so to speak, actually might help with the actual citation and the method section of the paper. And adding that then to the query store as a natural language explanation of the query would seem very promising. Yeah. Thank you.
Yeah. As I said, a bit beyond the scope of what we do, but we can do some, sorry, it's difficult to explain what we do in a short time. But we do abstract away from the details. So our language can talk to many different database. So yeah, we have a lot of power. Maybe we can continue this discussion somewhere else.
Absolutely, I'd love to.
Okay.
Yeah, it sounds like a great opportunity for maybe one of those EOS grants.
Yes, possibly. Yeah. I wasn't sure whether European included British though. So yes,
I think
that's a sensitive topic at the moment.
I think it does.
Yes.
Actually, I think it does.
Okay.
And you could probably find a European partner, but
Yes.
I don't want to say that, but I believe that the UK is still involved.
Good. Any further questions?
Oh, and Najla just said that the UK is okay.
Any further issues that we should address, double check? If not, I'd probably go on with the next parts, where I'd just like to very briefly run through this slide. Changing seems to be on a different focus again. Can't change the slides again, so maybe set the focus of the mouse pointer again on the slide deck away from the chat. Yeah, now it's working. So if you're planning to implement, or if you're doing it, just let us know. We would be really interested in learning more about that, and also to share the experience and the discussion. So that's an ongoing thing that we would like to continue. And now for some of the new stuff that is going on. So we have a new reference implementation that has been done by a colleague of mine. He's not here, so I'll just briefly present his slides, but what we are actually aiming for is doing a more extensive webinar on that specific solution in fall, in autumn. So basically what he did is he implemented a reference implementation for RDF-based data, which is basically with a main focus on supporting versioning of ontologies, because ontologies change, the knowledge they represent changes, and anything that uses ontologies, if you want to do anything reproducible and traceable there, requires that those ontologies are versioned and timestamped basically. And so he came up with a solution that is actually quite efficient, and I won't be presenting any of the evaluation numbers here, but how to implement that in a hierarchically nested structure to add the timestamps to it, and how then to also translate automatically the Sparkle queries that go against the RDF store, that how they are being transcribed so that they actually support the timestamping and versioning. And again, the goal was to keep it completely transparent from any other user interface or current program, so that the whole versioning and timestamping and the query adaptation happens at the repository side. And so what he set up is actually two implementations. One is a Python API that basically takes a Sparkle query, rewrites it to add the timestamps for any update statements, so that the triples are added with the timestamps as part of the regular update. And also when there is queries executed, that they're automatically transcribed and executed using the timestamps. So that's basically a Python API. And in order to test it more easily, he also set up a proxy server, where you basically, again, you contact the proxy server, and that proxy server basically is in front of the actual Sparkle endpoint that stores the ontology, that stores the RDF data. And it applies the API and does things transparently. And he has set it up with YenaTDB and GraphDB, two prominent databases for RDF data. And it's now being, tested and evaluated further. And I think the really exciting thing about that is that this would allow all ontologies to transparently become traceable sources for science, because currently it's actually extremely unreliable to use any ontology for any scientific study, because that ontology will change, that's for sure, over time. And then you can't reproduce an earlier study. You won't get the same subsets of data. You won't get the same annotations of data. You won't get the same semantic representations. If you now simply add timestamp when a study was being done, suddenly all that knowledge is transparently, but consistently reproducible. So I think this is going to be one of the most exciting developments we have been seeing in the recent month. Again, here is the link to the source code of the whole thing, the API and the proxy server. There is a paper that is currently under review, and I hope we'll be able to set up then a more extensive webinar with more technical details and with the original author present later this year, so that he can actually ask all the detailed technical questions. But if there's any immediate questions that I can try to answer, please let me know. I'll try my best to address them. No questions? Yeah, that's the talk. Yeah, Marcos just posting in the chat the link to a podcast that was prepared earlier this year, where Mark and I talked a little bit about how this whole thing came into being. Very nice. What do we call it? Fireplace chat on the whole history. Mark, if we have time at the very end, we can actually pull up the podcast. So that's a new reference implementation, so testing technology and rolling it out that way. Now I want to briefly present two very related but new pilot deployments that are being rolled out as services. One actually being rolled out as a database infrastructure across a number of universities in Austria at the moment. And the other one, again, being a reference implementation of a secure data infrastructure, but which borrows a lot of the ideas from here. So I go through them very quickly. DB Repo, it's a database repository system development is funded by the ministry in Austria, shared across a number of universities, which basically tries to set up a database infrastructure where researchers can host their databases and where there's a separation of concerns. So the IT infrastructure service provider takes care of the technical operation, backup, security patches, and the actual management of the data infrastructure, cloud-based deployment, OpenStack, so that it's scalable. Data stewards take care of the data stewardship tasks. So specifically with a focus on improving the fairness, we have links to ontologies for describing the measurement type. So temperature is not just a string in a column of a database table, but it's linked to the ontological concept of a temperature, and it's associated with a measurement unit, be it degrees Celsius, Kelvin, Fahrenheit. And again, that's via structured ontology. So it's really focused on these fairness for machines so that they can actually more easily find and interoperate with the data. And it obviously supports the data versioning and data citation principles as laid out in the recommendations. I don't want to go into details of how it works, but basically it's supposed to be, and it's being rolled out next year. We are now in the pilot phase, rolled out next year as a professional service then across those universities, to allow researchers to set up their databases and have them centrally curated and managed right from the onset of a research project, and have the databases curated and citable in a database environment rather than doing it under their own desk and then dumping the database post-project into some file storage, which renders the databases utterly useless, but which unfortunately for a lot of the long tail data still is quite common practice. Here I'm not talking about the big climate data centers and genomics databases that are professionally curated from the onset, but about the massive amounts of research data that is just being collected by some researchers somewhere for some project and then needs to be managed in some way or the other. So again, each query that is issued to the database is stored in a query store. And as Mark said before, you don't have to persist all of them. Basically, they are in a staging area, and the ones that you want to persist, that you want to assign a DOI or some other persistent identifier to, are then selected and stored permanently in the query store. There is a public demo instance that we have released where you can play around with it. I guess you can even upload your own data to the database for testing purposes, but that's one is being purged every 24 hours or every week, something like that, so that we don't run, a host of databases. But there's a few demo databases that you can interact with. And it's really for the long tail of data, so CSV file type data, but also live data streams. So we have measurement sensors connected to it that feed data live into the database. From the next pilot that we're going to do is river level monitoring, so water level monitoring and water quality monitoring that is continuously being fed in by sensor networks. Again, link to a paper that describes it, the public test instance, some documentation, and of course the source code if you want to set it up yourself or want to join the project of developing it further. And the second one, and I'll go through it right away, and then I'll take questions if you've got any, because it's tightly related, is a completely different setting in terms of mindset, but using very similar technology. It's OSTIP. OSTIP is a secure data visiting platform. And as was mentioned in the opening by Barend, data visiting is one of the key concepts that we will see come about in a number of settings, not just because of the sheer size of the data that just doesn't allow a few petabytes being copied over to any laptop for further analysis, where your code has to visit the data to analyze it. But in our case, specifically for sensitive data, and this might be privacy sensitive data, medical data, but it might also be just IPR related sensitive data or commercially relevant data that you don't want to give out of your hands and lose control. So what we've set up and have been operating for more than 10 years is a secure data visiting platform in the medical sciences for a very small group of researchers, very handcrafted solution. And what we did then recently is re-implement that and come up with a reference implementation that allows other institutions to evaluate and test such settings, because there's a number of such secure data visiting platforms being operated by different data centers, but very few of those have published how they are doing it and the structure and architecture. So that's something that we wanted to support with this implementation. Again, it's an fully open source based implementation that you can easily deploy in your own infrastructure as a reference implementation, and then obviously you need to fine tune it and target it to your needs. But basically the key concept why I'm presenting this here is that apart from all the physical security mechanisms and virtual firewalls and safeguarding the entire infrastructure, which is pretty standard technology, the key concept of it is that when a researcher wants to work with a specific subset of data for a specific study, they request access to that data. The data itself is stored on a completely isolated machine that is not connected to the internet. And if a researcher then gets granted access to that data, the query is somebody physically connects to that machine, extracts that data, and shifts it to a virtual machine that is then copied over to a compute environment, and then that connection is broken again. So this is really, for paranoia mode, basically a highly secure infrastructure with lots of other additional add-ons. And what we have there is that it's not only that the data is being extracted, you can then apply for each individual subset specific k-anonymity, L-diversity, T-closeness, anonymization techniques. You can apply fingerprints to the data, so it's tractable if data should ever be leaked. And then if you want to go, we haven't implemented this yet, further homomorphic encryption and data shielding. But again, the query is stored centrally. And in most cases, we recommend also that the query, so the fact that the subset was being extracted and used for a study, a lot of that information can even publicly be shared. And that allows closed data to become fair, because it's transparent that a researcher had access to a specific subset and was doing a study on it. And then it obviously depends on the setting how much you reveal in terms of information on their specific data set. Here's a link, a short depiction of the very first version of the architecture of that reference implementation, where I guess the only highlight that we have here is that we have a completely shielded off data server, with that connection usually being physically broken. And it's only temporarily when new data is being uploaded to it and when data is being sent over to isolated compute virtual machines that those connections are being activated. But the fact is that we then have the query store, and the query store is located outside the secure infrastructure. So that's basically public information that you can share, making highly sensitive and secured and closed data still fair, with clear guidance on whom to contact if you want to get access, and then clear access regulations. It obviously comes with a number of processes, how this whole thing is being implemented. But basically the key part is that if the permission is being granted, a subset of data is being extracted, and that metadata can be exposed publicly, whereas the rest of the research happens closely. Again, link to a paper and to the source code if anybody is interested on picking up that. We're currently discussing with other infrastructures to find out about commonalities and differences in the respective implementations. This is a reference implementation that you can deploy as virtual machines on one single computer. Real setups obviously will have separated physical machines and other safeguards. So that's the new directions we have at the moment. So the new pilots. Are there any questions for those? If not, then we'll take a short glimpse on some new ideas that are emerging, just to take a look at where this working group and where further adoptions might be going. And also for me, the exciting thing is to see how generic the recommendations are. So the new directions are two things. One is information retrieval systems. So basically the stuff that Google and the focus seems to be, so are doing. Typically when you retrieve documents from a document repository, so you have whatever repository of scanned documents, books, newspaper articles, whatsoever, if you select a subset of those documents for any specific purpose, medical records, patent information, in legal documents for due diligence testing, there is a reason why those systems usually use very trivial Boolean search, because that's the only one that is fully reproducible. A term does appear or does not appear in a document at a given point in time. More advanced retrieval models that have term weightings are not reproducible, because the moment you enter a new document, the term frequencies and document frequencies of all other documents change. Well, not the term frequency, the document frequencies of all the other documents change. And thus, the retrieval ranking will change. And so if you take a look at the top 100 documents, or if you select for a study from a document repository, first 5,000 documents that mention certain concepts, then these results will be different. So you can't reproduce more advanced ranking queries in such IR systems. Because, as I said, the document frequency changes if there is another document that has the same term, and this changes the math of anything that follows afterwards. Now, this is extremely hard to counter with, but it's a problem that we are facing in a number of settings. Whenever document collections are being used as basis for scientific studies, if you use whatever repository of Twitter feeds and you retrieve all tweets or the top 10,000 tweets in a certain time frame that mention a certain concept, then that top 10,000 ranking just doesn't work anymore if the document collection is changing. Same for business intelligence reports, online learning systems where you're learning with new documents being fed into. And wherever you want to have the results auditable, so patent retrieval, due diligence evaluations, and so on. Luckily, there were some people back in 2014, Hannes Mülleisen and his colleagues, who set up a retrieval system based on column store databases, and they could show that this was still reasonably efficient, not as fast-paced as the high-performance optimized standard retrieval engines, but still reasonably fast, meaning query times in less than a second for large document collections. And now, since they were using column stores, we are back in a kind of database world where you can version things much more easily than in the complex optimized index structures of conventional search engines. And so what we did was pick their concept and then identify different ways of how to add versioning information into these column store databases. So you have an edit and remove timestamp to the documents, and via the terms and dictionary tables, we could then recompute basically the TF-IDF values of any different at any given point in time. There is other database schemas where you actually add the TF value directly with a certain timestamp, so you can actually have that pre-computed, trades, storage for speed, basically. And that allows queries to become fully reproducible. And there's a current setup that we're rolling out now where you perform the live queries on a regular search engine, so Apache Lucene, for example, and where the query is then being stored in the query store, and the versioning and historization happens in the column store database, so that if you want to get back an older sample, you then go to the column store database to reproduce exactly the same subset and the same ranking. It's a bit tricky, but it works. So that's something that we're waiting for feedback for, but basically it does allow you to transcribe a standard BM25 query, for example, into a SQL statement where you select the respective documents where the edit timestamp and the remove timestamps are in a certain setting. And then once you have selected them, you basically recompute the score, matching exactly the way it was computed in the Lucene search engine. And then you sort them and provide them as a subset up to a certain limit, whatever you want them to retrieve. So a simple example of how this can be applied to actual document retrieval systems, because it does work for any kind of data. You can version any kind of data, you can version any kind of data representation. The question is just, what is the best way of doing it? What is the most efficient way and most flexible way of doing it? And obviously it is slower than standard Lucene queries, but depending on which way you implement it and which way you trade storage for query performance, you're in query ranges of 3 to 5 seconds, which is too slow if Google wanted to operate it on its live query system, but sufficiently fast for any document repository to handle. Any questions on that one? No? Everybody happy? Good. Then we move into a more speculative thing, and I don't have that many results to share here, but it's something that we wanted to start discussion on and actually think about it rather than having a solution yet. Pressure on AI systems is increasing because a lot of things have been and are going wrong in the deployment of these, and the European Union at least is now rolling out or proposing a new regulation on the deployment of high-risk AI systems. So it has a classification of unacceptable AI deployments where you're not allowed to use it, and high-risk systems. And for high-risk systems, there's a number of compulsory regulations that one needs to obey, mostly focusing on documenting procedures, but a lot on transparency, auditability, and tracing back on what is actually happening. And they also recommended to apply the same principles to less critical settings, because basically people are affected in any kind of exposure to automated decision making. And so one setting that's particularly challenging here is the regulations tell you what requirements you need to meet, but they don't tell you how to achieve these. And one of the requirements basically is you need to be able to track back the state of a decision that has been made. So in any instance that has been submitted to an AI system takes a decision, you need to be able to go back to it and investigate it. And this is fine for static models because you can save the model, but what do you do with online learning models? What do you do with systems that update their weights in interacting with their users? How do you trace the evolution of the learning curve, so to speak? And what we think might work, conceptually it definitely does work. The question is, does it work sufficiently well? Does it work sufficiently efficiently? That we apply the same principles, that we version the updates to the model's weights, for example, in these online learning batches. So when this model is being retrained, at least the final 2 layers, usually it's a fine-tuning adaptation that doesn't update weights all the way through a deep learning network, but only updates parts of it, to store those deltas, not just as a sequence that you then need to reactivate, but as actual versioned dumps, so that you can on the spot go back to a specific state of the model. And we obviously need to check whether this is faster and more reproducible than just keeping the sequence of data that has been presented and retraining the network from its initial state, which would be like a rollback in a classical database. So that's one of the ideas that we are currently toying with, seeing whether the same principles of timestamping and versioning and identifying the state by its state at a specific point in time actually can be applied reasonably efficiently also to such non-typical settings of, again, basically data identification, because a machine learning model is nothing but data. Everything that we deal and interact with is data. So this is still a bit speculative, but I just would like to raise the idea and see whether there's any feedback or comments from the community on this, or whether anybody has seen and considered doing something like that, or knows of other exciting settings, even though they might seem absurd in the first place, where we might deploy such things.
But the weight is part of the, not the data, the model, and the query is a different entity.
Mm-hmm.
Where do you put the weight?
So the question was for those online whether the weights in the model are not part of the data, they're part of the model. And not part of the query. I agree, but I see the training data is a database that needs to be timestamped and versioned, but the model is also data. The model, the weights are a type of data, so we can also store the weights, not in a database very likely, because that would be a very inefficient way of storing. So we are trying to find out what is the most efficient way of storing it.
A relation,
yeah.
Which is also an entity.
Yeah, and it's like the source code of the whatever Jupyter notebook that was used for training the model also is data that we can link. So we have the raw data, we have the source code in some GitHub, we have the model, the trained model stored in some other form, maybe as a file dump, which again is not storage efficient. But the idea is that all components that we use in research basically are data because it's digital.
It's very key to explainability. You can understand when bias might happen, you can track the weight.
This is exactly what so the comment was that this is key to explainability. And yes, this is what we are trying to aim for, to have all the components there, all identified by a single concept, which is the time at the local instance where it was being taken from. And that way one should at least have all the components in place in order to investigate, to have explainability, to identify bias, when did it emerge, why did it emerge, to allow those kind of investigations that are essential both for the consumers and users, but also for the ones operating those systems. So that would be the idea behind it. Again, a bit speculative at the moment. We know that it does work technically, but we also know that the simple solution does not scale for these AI models, because writing every state would just dump too much data and it would slow down the training process. But at least conceptually, it's a nice exercise, and now we need to see how we can make it work technically. Let's see where it moves. Does anybody else have any comments, statements, questions, ideas, wishes on what we should continue doing? Would you be interested in attending this session again if we held one at the next plenary? No, I should phrase the question the other way around. Would you not be willing to attend this session again at the next plenary? Who would not attend again? Simon only needs to phrase the questions correctly to get the answers that you want. Was it useful? Was it not useful?
Well, I can answer from the room.
Yeah.
I'm starting from scratch.
Mm-hmm.
So, well, not quite, but almost. We have large databases at the university where I work. And we have difficulties to get, well, to know how to give them a system to identify, basically. Mm-hmm. So this is why I'm here, trying to understand it. I understood the first bit, and the rest was a bit over my head.
Okay.
So I would be happy to listen to it again, but I feel that I need to sort of get some more information.
Which part was where it started getting confusing?
The pilots.
The pilots?
Too technical. I'm not a technical person.
Okay, yeah.
So I'm here to sort of represent people who are, because they're not here. So that was too difficult for me. But I'm guessing that the rest of the crowd probably more sort of into that.
So basically, in all the adoptions that we have been accompanying as a working group, it was usually a mix of people for each pilot that was there. So researchers who knew the data and the way they were using the data and the type of updates they were expecting, and so technical people who are running the actual hardcore infrastructure, the hard drives and that stuff, and then somebody from the data management or policy departments who basically understood how the data needs to flow and what are the requirements from an intellectual perspective towards the data, openness, closeness, the processes, the type of reproductions that need to happen, things like that. And it was usually teams of those three, plus finance was sometimes involved when it comes to then deciding on when should they launch an implementation study. But usually it requires at least all these three bodies on board to come to a meaningful design. And basically all that we did was accompany them and ask questions, because the solution then needs to be a local one, a deployed one. Finding out the best pilot that would match, seeing whether there is relevant pre-implemented components that one could use, or in many cases discovering that most of the stuff is already there in the institution already, and just nobody bothering telling anybody else because they didn't think it was relevant, which was really the most surprising effect that we had.
I'm just thinking about cases that we know, cases of AI bias, or, and then to go over the weight, for example, to see how changed. Just to make it less, I don't think that it's so speculative, the last correction.
Yeah.
I think that it would be really, I'll be happy to try.
Okay, happy to hear that somebody's interested in those more exotic topics on the AI versioning. I said, I do think it might work. The reason why I say it's speculative is because I don't have an implementation yet, and I know that the dump plain out of the box solution would not scale reasonably well. So that's why I think I'm pretty sure there is more efficient ways of doing it, and we have found some papers that deal with those difference tracking things for different purposes. So there is ideas out there of how to detect differences between models and how to store them with a minimal storage footprint and so on. So there is work being done on that. We just need to invest. These are all ideas that we have been starting thinking about a few months ago, basically. And this is why I still call it highly speculative. But yes, I'm convinced that technically it should work. The question is how practical it is. But I also see it as an exciting exercise in understanding how generic the concepts are.
And when you study that, you want to have real world data, not just synthetic data?
It doesn't really matter which data it is. Usually we use benchmark or prominent cases of whatever online learning systems. Usually not sensitive data, because that makes it hard to publish the results and share the results. So quite frequently benchmark data.
I think the AI applications has great promise, Andy. I mean, well, maybe phrase it another way. There's a great need for this. So if we can address that need fairly concisely, that will be very helpful.
Yeah, that would definitely be exciting. So I hope that by the next plenary, we might have made some progress on it and at least have a better understanding of the impacts. We'll definitely keep that discussion up and going.
It really is getting that what we're doing now is really going well beyond the concepts of citation. It's reference. It's precise reference to arbitrary subsets of data in a very abstract sense, like you were saying. The model is the data as well. Might be time to think about rejiggering the working group and where its focus goes.
Yeah, I mean, I think ultimately the intention was always identifying the state of the world at a specific point in time, so to speak, in the most generic way. Although that wouldn't have worked in the early days when we started the discussion. So that's why we started with data citation. But basically, it is ultimately about identifying that, yeah.
We have a question in the chat, and that I don't know the answer to, Andy. What are the links between this group and the Data Granularity Group?
I have to admit, I discovered that group a couple of months ago when I was preparing for this plenary. And so I need to take a look at what the state of discussion there is. Because as far as I understood from their description, they're really looking at how to define and describe the granularity of data and at which level to assign semantic assertions on the data. So it's, in my opinion, and I might be misinterpreting it, it's like the discussion that we had with the versioning group on, major and minor versions, which I see only as a semantic assertion on a specific state at a given point in time. And the Data Granularity Group also seems to be addressing different levels of granularity that one should refer to things. Ultimately, from our perspective, those groups take a look at the semantic aspects of it, whereas we take a look at the technical aspects of it. So whatever granularity is being provided as the finest one possible in a given data repository, that's a granularity that we can address. But this is an answer now without having discussed with the chairs of that working group.
Great. Well, I think we're out of time, Andy.
We're 5 minutes over time, and there's still some people around. Thanks a lot.
And people hanging out online too.
Well, the advantage of being online is you're not missing lunch because it's different time zones for you.
Yeah, we're going to bed.
Yeah, I've watched the sunrise. Well, I would have watched the sunrise, but it's cloudy.
Oh, more faces popping up online. Cool.
Thank you all. Thanks for
Thank you all for joining.
hanging through.
And if you've got any comments, feel free to reach out to us. Thank you. Have a nice night's sleep, morning day ahead of you, nice lunch and splendid afternoon. Thank you.
All right, ciao, y'all.
Bye.